Hello, this is Dr. Christy Patton-Lukes, a chemical engineering professor at Missouri S&T. We are looking now at Chapter 5 from our textbook, which is the second law of thermodynamics. And let's start by thinking about spontaneous processes. So this gas cylinder here, what would happen if I took and opened the valve? Yeah, the gases would leave the tank, right? It has a direction. The gas is going to go from the high pressure to the low pressure. I'm not going to get it to spontaneously refill the tank. If I took an empty tank and put it in the room, would all of those gases suddenly go back in and repressurize the tank? No, that's crazy, right? What about if I take some nice hot cookies out of the oven and set them on a cooling tray? What's going to happen? Well, obviously, they're going to cool. They come to ambient temperature. If I set them out on that cooling tray out on my kitchen counter, they're not going to spontaneously heat up. So one direction is spontaneous, the other requires some effort. So again, it has directionality. Or how about this one? Let's drop a dropper of food coloring into some water. The molecules from the food coloring are going to mix in. I am not going to wait long enough that they will unmix. This also has directionality. So all of these processes we were looking at, they have directionality. And that's also what we were calling earlier irreversibility, and still what we will call reversible or irreversible. So a reversible process is one that doesn't show this directionality. It also is going to represent the very best that we can do. In terms of our thermodynamic properties, this means that it will produce the maximum work output or will require the very minimum amount of work input. So let's talk for a moment about a gentleman, Sadi Carnot. In 1712, they invented the steam engine. And they had been tinkering with this, scientists, inventors, over the next 100 plus years, trying to really improve the steam engine, improve the efficiency. Efficiency can be defined a lot of ways, but I think a nice, easy to think about way of doing it is it's the ratio of the amount of work that we're going to get out, or whatever your goal is. But for an engine, we're trying to get power or work out of this engine. And it's a ratio of what we're getting out compared to what we have to put in order to get it. So what are the costs? And in the case of an engine, in particular a steam engine, it's how much fuel we put in, right? So that's going to be really heat transfer in terms of our thermodynamic properties. But it's a ratio of what we're getting out compared to what we get in. Now, Carnot wanted to maximize the efficiency of this engine, and so he spent years and years thinking of the best possible engine. And by 1824, he had proposed this optimal cycle. Now, his cycle, shown over here, if we start right here, we're going to take a material, we'll put it in a piston cylinder since maybe we know the most about closed systems, right? And again, we're thinking of a steam engine. So if we do this, then we can expand the material by adding heat to it, right? If you heat a gas, it will expand. And if we do that at constant temperature, it will be reversible and isothermal. Then his second step was to take this material and insulate the piston cylinder apparatus very well so that it's adiabatic, and then continue to let it do work adiabatically. So we put heat in at a constant temperature, and then we let the expansion continue adiabatically. Now then we need to return to our original state. So an engine, right, it operates so that the piston and cylinder keeps moving back and forth. And so we need to compress it. Well, let's do that by cooling the substance. And if we will take heat out of the system isothermally. That way it can be done reversibly. And then I need to finish the compression, and we will again do this adiabatically. And so he has 2 reversible and isothermal steps and 2 reversible and adiabatic steps. And these, he claimed, was the best possible engine that got the maximum efficiency. And in fact, people continue to look at this and found, in fact, he appears to be correct. Now, there was a lot of thermodynamic work going on during this time period. So fast forward another 40 years, and Rudolf Clausius helped develop a new property called entropy, and he was the one who named it. Entropy it means transformation. So how does work transform to heat? Or heat transform to work? So it's a transformation. And he named it this because it had that meaning, but also sounded a little bit like energy. And he wanted everyone to know that, no, this was absolutely as important as energy. People continued to do work with this. The other really important piece to this historical puzzle was Ludwig Boltzmann, 1877. He was able to see that if you look at the configuration of molecules in a fluid, okay, that entropy was related to how those molecules were positioned in space. And he essentially found that there were a lot more ways that you could be disordered, high entropy, than there were that you could be ordered, which was low entropy. And if I, look, you can come visit my desk any day, and you will see that my desk is usually high entropy, unless I've put in an awful lot of effort, and then I can get it to be ordered in that lower entropy state. So, but this becomes the basis of statistical mechanics. And statistical mechanics and thermodynamics are highly intertwined. And if you take physical chemistry classes, when you take thermodynamics too, you'll see more of statistical mechanics. But so entropy becomes really the heart of how this came to be. Now we're going to define entropy so that it is as a differential, the change in S is entropy. I can't explain that choice, sorry. It is the change in our heat transfer for a reversible process divided by temperature. Now, here's the trick. ds means that entropy is a property and it is independent of path. But the dq with the squiggle dd, heat transfer is path dependent. So we are defining this path independent property, a state property, based on a reversible path dependent process that isn't even possible, right? Reversible doesn't even happen. So it's based on this. And so we're going to base it on really a hypothetical process. It's not that I have to be able to actually perform this process. It's that I need to be able to imagine the process. So what we will be looking at in this chapter is what is the entropy change of the universe. And so we're going to be looking at that. And basically, this means we're going to need to look at the entropy change of our system or our process and its surroundings. In our next lesson, we're going to be looking at some special cases that will provide a lot of these answers. We're going to look at a reversible adiabatic closed process and then an irreversible adiabatic closed process. And then we'll come back and look at that Carnot cycle with a little bit more depth, at which time we'll finally be ready to develop the second law. Thank you very much for your time.